Good morning friends. We will continue with our earlier discussions on linearity of systems. As we had mentioned, a linear system will have the property like this. Mathematically we can write the property like this. If we excite a system by an input x1t, it can be either a voltage or a current, and the corresponding output is y1t. Similarly, if we excite it by an input x2t and the corresponding output is y2t, then any combination of x1 and x2, say a1 x1 plus a2 x2t, will result into a1 y1t plus a2 y2t if the system is linear. This is the principle of superposition. Now, sometimes you are given the system equation in the form of differential equations. How do you determine whether a differential equation is a linear differential equation or not? Suppose you are given, I will give you a simple example, say d square x by dt squared plus 2 into dx by dt minus 3 into x is equal to some forcing function f1t, maybe sin t, sin 4t. Another equation, d square x by dt squared whole squared plus 2 into dx by dt minus 3x is equal to sin 4t. The third equation is dx by dt, sorry, d square x by dt into t plus 2 into dx by dt minus 3x is equal to sin 4t. d square x by dt square plus 2 into x into dx by dt minus 3x is equal to 4t. Now, out of these, which one will be linear, which one will be nonlinear, which one will be representing a nonlinear system? Yes, first one, let us examine one by one. First one, is it a linear differential equation? Linear differential equation, the right hand side is sin 4t. Is it a linear equation? Is it a linear function? No. This is a forcing function. What about this side? They are all linear elements? They are. So, is it a linear differential equation? It is. The forcing function, whether it is sin 4t, log t, root t, does not determine the behavior of the system. Forcing function is external to the system. It is, this input is external to the system. So, the right hand side, the forcing function here can be anything. Now, this side, all these elements are linear. When we say linear, that means the variable, the dependent variable x or its derivatives, they all appear in a linear form. Okay. Here d square x by dt square is squared, so it is in a nonlinear form. Similarly, in this equation, the fourth one, it is 2x into dx by dt. So, dx by dt gets multiplied by x, alright, whether it is x into dx by dt or x squared or d square x by dt whole squared, okay, like the second equation, these are all nonlinear equations, nonlinear form of x and its derivative. What about this one, the third equation? here it is multiplied by the independent variable. So it is a linear time varying system. It is linear time varying system, but it is not nonlinear. Okay. So you must be in a position to identify a linear system from a nonlinear system. This is also a linear system, but it is having a time varying coefficient. A very nice example of a linear time varying system will be, say, a furnace. A furnace. You have the brick lining. Okay. If you start an experiment now with so much of input of fuel, say, so much of charge kept in this identical charge. If you perform the experiment, say, today and tomorrow, there is not much of a change in the furnace behavior, furnace characteristics. So if you want to write, say, the heat flow equation, you will find the equations are identical. But after 8 or 10 months, say, over the use of the furnace, the brick lining, the fire brick lining will gradually get damaged, alright, there will be aging. So the thermal property of the brick lining will be changing. Periodically you have to go for maintenance, you have to change the brick lining, and after 10 months or so, if you perform the same experiment, you will find the heat flow equations will be different, because the resistance, the thermal resistance has changed over time. So it is an example of time varying coefficients. The system differential equations may be identical, but with time varying coefficients. So sorry, whenever the elements like R, L, C, etc. are suffering a time varying change like aging, you have time varying differential equations of this type. Even though the system is linear, it is not nonlinear, but there can be coefficients which may change. Now a resistor, pure resistance, it is linear time invariant system, it is an oversimplification. Alright. People had conducted some simple experiments over a certain range of temperature, the resistance virtually remains constant. So we simplify the model by a simple linear relationship, V is equal to R into I. But actual resistance may be varying in a nonlinear fashion. Alright. As the current increases, the resistance may also change. There are many nonlinear resistances in day-to-day use. For example, a bulb, the filament of a bulb, if you change the voltage, current also changes. If you take the voltage by current ratio, it is not fixed, it changes. For example, for resistance, the characteristics, the ideal linear resistance, say this is a low value of resistance, if the characteristic is like this is a high value of resistance, and you may have sometimes, okay, I draw on this side, if you have performed any experiment on the bulb, filament bulb, incandescent bulbs, depending on the type of filament, it can have a characteristic like this or this. Here the resistance, sorry, this is the voltage, say. The slope represents the resistance value, so resistance keeps on falling in this case. Okay, voltage by current ratio does not remain same. In the other case, it may increase. Okay, so this is the example of a nonlinear resistor. Best example is incandescent lamp. So we approximate them to be linear for small values of current, or we linearize around an operating point. Say if this is an operating point, so around this point it is, the slope is taken as the resistance. or we define as incremental resistance. Suppose this is V plus delta V, this is V and this is I, this is I naught plus delta I, this is say V naught and I, V naught and I naught, V naught plus delta V, I naught plus delta I. So, the slope approximately is delta V by delta I at the working value V naught I naught. So, this is dV by di. So, the resistance, incremental resistance, is basically the slope of this Vi characteristics at an operating point. Similarly, for an inductance, how do you define an inductance, by the way? How do you define an inductance? Inductance is, it can be defined in two ways: time derivative of current and the corresponding voltage induced. A question that I very often ask, and I would ask you also: does a straight conductor carrying a DC have an inductance? Does a coil carrying a DC have an inductance? Does a straight conductor carrying an AC have an inductance? Yes, can you tell me? A straight conductor carrying a DC, will it have an inductance? The first thing that comes to your mind, inductance means L di by dt will be the voltage. You are used to think like that. So, the voltage, since it is carrying DC, so the voltage induced will be 0 because there is no change in current. So, I give an example: you have a mass, you apply a force, there is an acceleration. So, what is the mass? Yes, mass is force by acceleration. Now, you do not apply a force, so there is no acceleration. Does it mean the mass is not there? Mass is there, it is irrespective of the force applied. So, inductance is the property by which the conductor tries to establish the flux lines whenever there is a current flowing through it. So, whenever you have a current, there will be a flux established by the very property of inductance. So, it is the flux linkage, flux, number of flux lines, if you can count them from the conductor body to infinity. So, number of flux lines divided by the current will be the inductance. Now, obviously, it is not so easily measurable. I mean, it is difficult to measure this, but if by some means you can measure the flux lines established, then that will be giving you the inductance. So, it is immaterial whether you are passing a DC or an AC. Only advantage is for AC is this, that whenever there is an AC, you get a voltage induced which will be proportional to L di by dt, and you can compute the inductance. So, it is only for our computational convenience that we try to measure the inductance with the help of AC. But when there is a DC, inductance is there because flux lines are established. So, any straight conductor, because current is always associated with the magnetic field, so any straight conductor, the moment you pass a current, will always have flux linkage, and hence there will be an inductance, however small it may be. So, for all practical purposes, a straight conductor does not have a perceptible inductance, especially when we deal with very low frequencies. When you go to very high frequency, then the inductance will give rise to quite a substantial voltage drop if you pass a current of a very high frequency. So, an inductance will be present whether it is a straight conductor or a coil, whether it is carrying AC or DC. Okay. For example, when you go to the market, to buy an inductance. You do not say I will be using it for AC, please give me an inductance to be used for an AC. You do not specify this is 2 millihenry, 3 millihenry, you specify only the value in Henry. I want so much current rating and so much inductance value, a coil. So an inductance will be given by this ratio if it is a linear one. There is flux linkage per unit ampere. Now it is not necessary that it will be always a characteristic like this. There can be inductances where the variation of the flux linkage may be like this. Can you cite an example? This is a nonlinear characteristics. That means once again here also the flux linkage per unit ampere keeps on changing with the value of I, So can you cite an example? For example, the flux linkage in a coil where you have a ferromagnetic core which gets saturated after some time, okay, you do not get an additional flux per unit change of current at the same rate after some time, okay. So here the inductance value keeps on changing, once again the slope as you have seen earlier dV by di, so it will be incremental inductance which will be dψ by di, okay. So flux linkage and the current, instead of pure ratio you have to have the derivative dψ by di, okay. So that will be the incremental value of the inductance, that is at any operating point what is the slope. Capacitances normally are linear, capacitances are linear. There can be imperfect capacitances, then of course at different frequencies you have to have a proper representation of the leaking resistance, otherwise a capacitive element is linear. There can be different types of nonlinearities that may be present in a physical system. So before we go to networks in general, we will be discussing about mathematical as well as physical nonlinearities that are present in most of the physical systems. One of the most common type of nonlinearity is relay type. A relay type of nonlinearity. A relay type means where the input and the output variables are related like this. That is y or fx, if I write fx as output is equal to f naught, this is f naught and this is minus f naught. If x is greater than 0 and is equal to minus f naught if x is less than 0. This is relay type. There is another nonlinearity, that is relay with deadband. Relay with deadband. There is a deadband after which only the system responds. So you have x naught and minus x naught as threshold. So below this threshold value of x there is no response, it is 0. So fx will be equal to 0, okay, if x is between x naught and minus x naught, is equal to f naught, this is again f naught, this is minus f naught. When x is greater than x naught, equal to minus f naught when x is less than x naught. Okay. So, this is relay with deadband. Then you have fixed deadband only. Fixed deadband only. Here, beyond this point x naught, the relay output is proportional to the input. The effective input is this much, x minus x naught. So, this is giving you the output accordingly. So, this is fx. Similarly, on this side, so fx equal to some k times x minus x naught when x is greater than x naught, equal to minus k times x minus x naught. Correct me if I am wrong. If it is x minus x naught, will that be all right? It should be x plus x naught. It is minus x naught, mind you.
Slope is positive.
Slope is negative or positive.
Positive. It should be positive, sir.
Slope should be positive. Okay. Then x minus x naught is all right. Is that all right? When x is, then there is no difference. Then there is no difference.
But difference in the values of x.
X naught was there, now it is minus x naught. So, I should replace it by plus. No? Is it all right? So, when x naught is in this position, there will be an output. Okay. Next, you have fixed deadband, this one, and then you can have deadband. Okay, we'll take that later on. Let us see hysteresis. Hysteresis type of nonlinearity, an ideal hysteresis is like this. So, hysteresis type of nonlinearity is like this. Say this is x1 minus x1 and this is fx. So, fx I will write on this side, fx equal to f naught, this is f naught, if x is greater than x naught and x is going this way, okay, x is greater than x1, x is greater than x1, okay, because we are using x0 earlier, now we are writing x1. If x is greater than x1 and x is increasing, I will show this way, this is the direction for x positive, and then equal to f0 if x is lying between minus x1 and plus x1, okay. Is that all right? And x is moving in this direction. Why is this direction so important? It is obvious, at this value of x it is double valued, it can have either this value or this value. When is it having this value? When x is receding, x is going this way, alright, and when will it be in this position? When x will be increasing. So the direction, it is a direction sensitive value, it is a double valued function, it can take either this value or that value. So that will be specified by the direction of variation of x, okay. So similarly equal to minus f0 if x is less than minus x1 and x is going in this direction, equal to minus f0 if minus x1 x1 when it is in this range but x is increasing and x is going in this direction, alright. So these are some of the types of nonlinearities that we have discussed. You can also define another nonlinearity, hysteresis with dead band. Hysteresis with dead band. So I show you only the nature of variation and leave it to you as an exercise to define the function mathematically. So it follows a path like this. As x varies, it takes this path and then it gets saturated at f0. When you are retracing back, when you are reducing x, it follows this path and then it should have been yes, along this. So if I mark it as x1 and x2, if they are identical, then this will be minus x1 and minus x2. These are the threshold values, okay. So when again you are increasing x, it remains at f0, minus f0, then follows this path, then from here it goes to x2. So from minus x1 to x2 it remains 0. In the return path from plus x1 to minus x2 it remains 0, okay. So you please try to define fx in terms of different ranges, okay. Then there can be another type of nonlinearity, diode type, where you define the diode characteristics like this. this side the breakdown is at a very high value, whereas here it starts conducting. So, this is a dud type of nonlinearity, it is not to the scale as such. And then you have saturation type of nonlinearity. Like this, they may be symmetrical. In all these nonlinear functions that we have discussed, it is not necessary for a physical system to have a symmetry in the nonlinearity. Sometimes this side x naught, this side it can be x naught dashed, it can be something else. So, there can be asymmetry in their properties, in their characteristics. Next we come to dot convention of coupled coils. What should be the dot convention for coupled coils? Two coils are coupled. Let us assume ferromagnetic core is used and two coils are wound over it. To simplify the matter, let us see two coils in the same sense. We have got two coils like this, having number of turns N1 and N2. Okay. There is a resistance connected here, R1, resistance R2, and there is a current I1 and I2. The terminals are noted. We mark them as 1 1 dashed and 2 2 dashed. Okay. Now suppose from a source V G we try to send a current I1 through this coil N1. It should have been like this. Anyway, I was thinking of putting another turn anyway. So current is going like this, and suppose that establishes a flux phi 21 in this direction at some point of time. Then what should be the positive sense of the current? If I short this, if there is a current that is establishing a flux phi 21, which is established by I1, then this will try to, this coil, if it is shorted, it will try to send a current in such a way as to oppose this flux, is it not? That is by Lenz's law. So any shorted coil will try to circulate a current so as to oppose the very establishment of the flux, that is to oppose the cause. Therefore, I will term this as a positive current when this is positive in coil 1. Okay. So if coil 1, this terminal is noted with a dot, that means current is entering from this terminal 1, leaving through 1 dashed, then in the secondary coil current is flowing from 2 and going to the external circuit from 2 to 2 dashed. Is that clear? That means when a coil is shown 1 1 dashed and I put a dot here, that means if I excite this coil, 1 will be trying to send a flux phi to 1, and correspondingly a shorted coil will try to send a current from 2 to 2 dashed, if this is also shown by a dot. Okay. Alternatively, if I excite this coil by sending a current from here, and if I remove the source, if I short circuit this coil externally, then a current through this will try to force in an induced current which will be going from 1 to 1 dashed in the external circuit. If I inject a current from 2 inside the coil 2 to 2 dashed, then current from 1 will go to 1 dashed through the external circuit if this is shorted. Okay. So this is the convention that we follow for the coils. Now I pose a few questions before you and see what would be the nature of variation of different quantities. Suppose I have R1 and R2, some fixed resistances. What would be the variation of the currents, flux, voltages induced and so on? We have applied Vg, okay, at time t. We have just switched it on at time t equal to t0. So it is a step input of voltage. That means we are giving a DC supply here. We are just switching on the supply, DC supply across this coil. It is having some finite resistance. Okay. What will be the nature of variation of the current? I1 will be how much? Suppose this is kept open, this coil is not there, then at t equal to 0 it will go on like this, just like an any inductor RL circuit. Okay. This you have studied in first year class, principles of electrical engineering. You have studied simple RL and RC transients. So it is behaving like this. What will be the nature of variation of the flux phi 21? It is also identical. It is proportional to the current I1. So it will be like this. What will be the open circuit voltage? If I keep it open, what will be the open circuit voltage? Voltage across this secondary coil.
N1 by N2.
Voltage across this coil, what will be its nature? N1 by N2, etc. I understand that will be only giving you a ratio. But what about the voltage? How will it change? This is T0. So before T0 nothing happens. After that, as soon as you switch it on, the current keeps on increasing. So flux is also increasing like this. So what is the voltage induced? It will be N2 times d phi 21 by dt. So it will be depending on the slope, is it not? So how is the slope changing? Initially the slope is this much and gradually it is becoming 0. So, if you apply DC supply onto a transformer primary and you measure the secondary voltage, finally it will come down to 0. It will start with the maximum value and then it will gradually come down to 0, because the slope here will be 0. Is that all right? So, this is V2 with respect to time. Now, I pose a few questions. If R1 is 0, sketch the three quantities I1, phi21, V2 and also I2 if I short it. So, R1 is 0 and R2 is 0. That is, you have to compute or you have to sketch I1, phi21, V2 and I2. Next case, when R1 is 0 but R2 is not equal to 0, R2 is finite. And thirdly, when R1 is not equal to 0 but R2 is 0. Okay. Another set of interesting questions I want to pose before you is, what if the current I2 would flow in the opposite direction? If the current flows in the opposite direction, what happens? Why can it not flow in the opposite direction? Next, what would be the value of I2 in case I1 is a DC, that is a steady value? If I1 is a steady value, what will be I2? And so the questions are, if current I2 flows in the opposite direction, can it ever flow in the opposite direction? Next, if I1 is a steady DC, steady current, that is DC, what will be I2? And what would be the flux phi21 when R2 is 0 and R2 is infinity and R1 is not equal to 0? What would be phi21 if R1 is not equal to 0 and R2 equal to 0 and next infinity? Infinity means open circuited. What would be the values? Okay. One or two we will discuss here because they are very relevant. Sometimes by mistake you may put a DC supply onto a transformer, all right. Transformer is open circuited. Suppose the transformer is open circuited. So what happens to the transformer? Or the transformer you are applying, say you are going for a short circuit test, transformer secondary terminals have been shorted and you are supposed to apply a very small AC voltage on the primary. Instead of that you apply a DC. What happens? So this is a situation when, say, when this side the secondary side is open. If you apply a DC, it is a simple RL circuit. So after some time the current will be coming to a steady value like this. So this current is decided totally by the resistance and the voltage supplied. So voltage by resistance will be the current. If you apply a very large amount of large value of voltage, say 220 volts DC, and the current resistance value is small, then it will be damaging the winding, it will burn out. So the voltage applied decides the level of the danger, that is the chances of the winding getting damaged will be very much controlled only by the resistance value, which is normally very low. And what happens to the flux? Flux also goes on increasing like this. So just now we have studied, we have discussed the voltage on the secondary side will be varying like this. Now suppose this is shorted, the resistance is not there, or even if there is a resistance, if there is a resistance here, that will circulate a current, that will try to circulate a current, and that current will be trying to oppose the very cause. So it will try to oppose the establishment of the flux. So what happens to the primary? What happens to this side? Current I1, will it be more or less? Will it be more or less? If I short it through a resistance, why? Phi 2 it will try to re-establish this flux. Why? Why should it be re-established? It will, I2 will try to oppose the flux. It will try to oppose the flux. So will that modify this characteristics like this? This is what you anticipate. That means it will be going like this. Is it all right? You think of the situation in a transformer equivalent circuit, if you have studied already. The equivalent circuit, that is on the load side, now you are having resistance R2. Earlier it was kept open. Now you are putting a resistance R2. That means in the equivalent circuit you are trying to provide a path, alternative path through that secondary coil. So the total current increases. Earlier it was only the magnetizing current, now you are offering another path, so the total current will increase. Okay. So the current I2, I1 will be having a higher slope like this. So it will be reaching that value very fast. Okay. If you have a resistance here, instead of shorting it directly, if you have a resistance here, of considerable value, so it will be somewhere in between. If R1 is 0 and R2 is 0, if R1 is 0 and R2 is 0, what happens? That is, across an inductance, if I switch on a supply as a DC voltage, if I apply across an inductance, pure inductance, there is no resistance, what happens to the current? It is L di by dt, which is constant, V. So if it is L di by dt, which is constant, that means I will be constantly increasing. It is integral V dt. Okay, it is proportional to integral V dt. So I will be constantly increasing. That means you will get a current that will be continuously increasing, and that will cause a secondary current also in the reverse direction. that will also be constantly increasing. So both primary and secondary currents will be increasing continuously. Okay. So this is a very interesting situation. For example, sometimes when you apply a sudden change in the voltage, say an impulse, pulse voltage, in a pulse transformer you get sudden changes, and then though the voltage is there is no change, alright, there is no change, so on the secondary side there is no output. Whenever there is a change, there is an output on the secondary side. So this principle is used in a pulse transformer. Okay, thank you very much. We will continue with this in the next class. Good morning, friends. Yesterday we discussed about different connections of voltage and current sources, and then we discussed something about nonlinearities, different types of nonlinearities, then dot convention, and we will continue with that. The dot conventions that we adopted yesterday, I will just repeat. If you have a core like this, if you are having a coil, say coil A or coil 1 dashed, and another coil having the terminals 2 dashed, you see the coils are wound in the same sense. The coils are wound in the same sense. Then if the current, if I call 1 as the starting terminal, 1 dashed as the finishing terminal, similarly 2 as the starting terminal, 2 dashed as the finishing terminal, if current through terminal 1 enters into the coil, okay, like this, and current through 2 also enters through this coil, then both of them give rise to a flux in the same direction, alright. Or in other words, if we connect this with the source and if we short circuit this one externally, the current here will be flowing out of this terminal and entering through 2 dashed, alright, because it will be having, by transformer action, okay, if you are having an alternating voltage, say, applied here, then the current here will be going in this direction. Okay, that means what? It means that if the coils produce identical fluxes when they are excited separately, then those terminals, the starting terminals, will be shown by dots. That means a current entering here corresponds to current entering here from an external source. They are identical, that means they give rise to the flux in the same direction. This is easy to remember, alright. Now I give you an example. You try to find out whether this is this particular coil, just 1 minute, this particular coil arrangement and the dot conventions are correct. You are having a toroid with a central limb. Okay. Now you are having volt supply voltage here and measure the current I1 after shorting this. So how much is it? It is the admittance seen from 1 dashed under this condition. So it is 2 parallel elements YA and YC. Okay, is it not? ZA and ZC are in parallel, so you add their admittances, YA plus YC. Very good. Similarly, y22 will be yb plus yc when I am shorting this side. What about y12? What about y12? How do you measure y12? y12 is I1 by V2 when V1 is 0. So I short circuit this and then measure the current here when I am applying a voltage V2. So y12 is I1 by V2, I1 by V2 when V1 is equal to 0. And how much is that? By convention, I1 is positive when it is flowing in this direction. Now when I am shorting this and applying a voltage here, there will be a current that will be flowing like this. This current does not affect this, does it? This current is independent of this side. I am measuring only this current, and since this is short, so this is redundant. There is no current flowing through this. All the currents will be flowing through this. So the current flowing through this side will be through YC and then through this zero impedance. So how much is the total admittance? YC. Only YC. What about sign? Because the current is flowing in the opposite direction, so it will be minus YC. Okay. Now, if you are given these Y parameters, there is a black box given to you. I have given you 2 ports, 4 terminals, and I ask you to perform this short circuit test. That is, you short circuit one side, 2 dash, make a measurement from this side, make the measurement of the current on the other side, voltage from this side, voltage and current at this end, and so on. That is, you measure V1, I1, I2. Again, excite the other side, short circuit this side, 1 dash, apply a voltage V2, V2, I2 and I1. Okay. So you will get all the 4 quantities. This is also I2 by V1 by the same logic when V2 is 0, when I short circuiting this, applying a voltage and measuring this current. Is it all right? If you are given these parameters, but inside I don't know what it is, there can be number of elements interconnected. Okay.